Assalamualaikum and hi, my name is Muhammad Hazim and our group from section 5 group 10 will present mathematic modeling of dynamic system applying differentiation calculus to traffic density and reactor heat transfer. Our group member is Ani Aiman bin Alias, Khairul Yap, and I Muhammad Hazim bin Zakwan and Muhammad Shahid Darimi bin Amran. For question 10.1a is what time does the traffic density stabilize? This is the equation t square plus 4 over 100t. For the solution is first step is we make the equation into two parts is t square over 100t plus 4 over 100t, make it as a 2. For second step is we differentiate the equation into t square minus 4 over 100t square. For step 3, we assume d per dt equal to 0, and for step 4, we use 0 equal to t square minus 4 over 100t square. For this equation, we will get t equal to 2.
Assalamualaikum, my name is Karuya AA251144. Now, let's interpret what this derivative tells us about real-world highway traffic. By analyzing our derivative d bar equal to t square minus 4 over 100t square, the critical turning point occurs when the numerator equals 0. This happens exactly at t equals to 2. Now, if we look at the screen, let's start by making the graph first. Ft equals to t square plus 4, don't forget the brackets, divided by 100t. And this is how our graph will look like. Before 2 hours, the numerator is negative, meaning d bar is lower than 0. The traffic density is decreasing and the congestion is clearing up. Exactly at t equals to 2, the derivative is 0. This represents our minimum traffic density points. After 2 hours, the numerator becomes positive, meaning d bar is more than 0. Traffic density is increasing and the congestion is building back up. Let's continue with our graph. Let's use y equals to 0.04 and let's label up. As you can see on our Desmos graph on the screen, we verified this behavior perfectly. By plotting the function alongside a horizontal tangent line at y equal to 0.04, we visually confirm that this label is the absolute lowest point of traffic density. To the left, the curve slopes down, while to the right, the curve slopes up. Thank you.
Hi, my name is Ani Aiman bin Alias and my metric number is AA250924. Today, I want to present our case study 2, Chemical Reactor Thermodynamics. The main question asks to find the time t when this function reaches its critical state. In calculus, a critical state happens when the rate of change is 0. Therefore, our mathematical condition is to set the derivative to 0, which is d per dt equals 0. So, our first step is to figure out how to differentiate this function. Please look at the slide. We are given the heat transfer function of reactor, which is hash bracket t equal t e power of 0.1t divided 1 plus t power of 2. Alright, to find the derived, let's look at the second slide. Because our function is a fraction where both the top and bottom contains the variable t, we must use the quotient rule. You can see this a top and the slide is as our master formula. U prime v minus u v prime divided v power of 2. Next, we break our function into the two parts. First, the numerator component u. We say u equal t e power of 0.t because this is multiplication, we must apply the product rule. This concept is simple. We just copy the term back but switch which one we differentiate. First, we differentiate t and copy e power of 0.1t plus we copy t and differentiate e power of 0.1t. This is given us u prime equal e power of 0.1t plus t bracket 0.1 e power of 0.1t. Second, the denominator is v. V equal 1 plus t power of 2. The derived for this is very straightforward, which is give us v prime equal 2t. After we determine u prime, v and v prime, we then arrange them according to the quotient rule formula to get the derived mapping, which is d per dt equal e power of 0.1t bracket 1 plus 0.1t bracket 1 plus t power of 2 minus t multiplication e power of 0.1t bracket 2t divided bracket 1 plus t power of 2 bracket power of 2. Finally, map all the space u prime, v and v prime into the master formula after substitute the value and simplify the algebra. We get the final simplified derived shown at the bottom. D per dt equal e power of 0.1t bracket 1 minus t power of 2 plus 0.1t plus 0.1t power of 3 divided bracket 1 plus t power of 2 bracket power of 2. This is question that we'll set to 0 to explain the calculation step and solve for t. I will now pass the presentation to my partner. Thank you.
Assalamualaikum. My name is Muhammad Syahir Dadimi bin Amran, Geometry AA251380. Today, I will explain the method to determine the time t when the chemical reactor has transfer reached a critical state. So, first, to find the critical state, we need to find the point where the rate of change of heat transfer is equal to 0. Therefore, in step 1, we set the equation as d per dt equal to 0. This means the heat transfer is no longer increasing or decreasing and the system has reached a critical point. Next, in step 2, we substitute the given equation and obtain the expression shown on the slide. The equation consists of three main parts: the exponential function, the numerator, and the denominator. To solve this equation, we need to analyze each part. The exponential term, which is e raised to the power of 0.1t, is always positive. The denominator, which is 1 plus t to the power 2, or bracket and power 2, also cannot become 0. Therefore, the only way for the whole equation to become 0 is when the numerator is equal to 0. So we isolate the numerator and get the equation 0 equal to 0.1t to the power 3 minus
t to the power 2 plus 0.1 t plus 1. This is a cubic equation because the highest power of t is 3. To find the value of t, we solve this cube equation using mathematical method or calculator. After solving the question, we obtain the result. That's meaning is final answer. T equal to minus 0.9126 minutes. So, in conclusion, by setting the rate of change to 0 and solving the resulting equation, we can determine the critical time for the reactor heat transfer. Thank you.